So continuing to look at some different things involving population distributions and sampling distributions, some different terminology here that we're going to look at. And it's very important that we make the distinction between these three things here. So a population distribution gives the values of the variable for all individuals in the population. The distribution of sample data shows the values of the variable for all the individuals that are in the sample. And then a sampling distribution, which is what we're going to talk a lot about, shows the statistical value from all possible samples of the same size from the population. So population distribution is the values for each of the individuals in the population. The distribution of sample data is the value of the variable for all the individuals that are in the sample. And the sampling distribution shows the values for all possible samples of the same size from the population. So one of the activities that we're going to do in class has to do with a bag of chips where we have 100 red chips and 100 blue chips, and what we're going to do is we're going to take a random sample of 20 chips from the bag. So the population distribution for something like that would be all of the chips that are in the bag. So we have 100 blue and 100 red. The distribution of sample data would be the results that we get from taking our samples of size 20. So here's an example of one of the samples that I did on my own, and the results that I got for that were 12 blue, 8 red. Here's another sample that I took on my own, and this one had 11 blue and 9 blue and 11 red. And then this is a third sample that I did, and this one had 7 blue and 13 red. So one of the things that we'll look at when we do this is the proportion of chips that you get that are red. And then this right here is the sampling distribution. So meaning that if we were to do this size 20 sample for all possible samples that you could take from the bag, this is what the sampling distribution would look like. So just notice, since half are red or half are blue, the center of this graph appears to be around 0.5. So the proportion of red chips that we would get should be somewhere roughly around 0.5 as far as the center of that sampling distribution goes. So the question here, it says Mars says that the mix of colors in its M&M's candies is 24% blue, 20% orange, 16% green, 14% yellow, 13% red, and 13% brown. Assume that the company's claim is true. We want to examine the proportion of orange M&Ms in repeated samples of 50 candies. And the question says, what's the population distribution? And we're going to identify the individuals, the variable, and the parameter of interest here. So in terms of identifications, the individuals would be what it is that we're talking about. In this case, that would be all of the M&M candies, and then the variable in this would be the color. That's what's changing in terms of what I could choose that's in the bag. I could get any one of these 6 different colors. And then for the parameter of interest, what we're going to measure here, because it says the proportion of orange M&Ms, that's what we're interested in finding from our sample. And then in this case, the sample size for this, okay, it didn't ask for that, but the sample size for this would be 50 candies. Also important to note when we're talking about sampling distribution, what the sample size is. Same sort of thing here with number 2. Imagine taking a simple random sample of 50 M&Ms, make a graph showing a possible distribution of the sample data. So for something like this, okay, what we would have is, I think the easiest thing to do for this is to make some sort of graph that kind of illustrates kind of like what we did. Let me sort of back this up here and clear this off. What we kind of did here with the values that we got from the sample. So this is something that you would want to make as a graph for something like that there. But in terms of the, sort of fast forward here, in terms of the sample, okay, if we had a sample where there were 11 orange M&Ms out of 50, we would say that the p-hat value was 11 out of 50, which would be 0.22. So that's just some different things with the value of the statistic that comes from that sample. And then the last question with this says, which of the graphs that follow could be the approximate sampling distribution of the statistic? So if we go back to what they were describing as the orange M&Ms. They're saying here that 20% of the candies would be orange M&Ms. So with this here, what I'm looking at is a graph, or 16, or is that 16? 20%. 20% would be orange. So what I'm looking at here in terms of a sampling distribution is a graph that looks something like this here, where I have a dot plot because I'm measuring the frequency with which my percentages occurred within the samples, and I would have a center here that's roughly around 0.2. Okay, that's what I would expect to happen if in fact the 20% claim was in fact true. So in terms of describing a sampling distribution, okay, one of the things that we want to do, or one of the things that we're looking at, is how trustworthy is the statistic as an estimator of the parameter? How trustworthy is the results that you get from your sample to estimate something about the population? And one of the things that we look at when we're describing a sampling distribution is we want to look at the center, we want to look at the spread, and we want to look at the shape of what it is that we have as far as a sampling distribution goes. So just kind of revisiting the other example that we talked about with this, and it says in the chips example we collected many samples of size 20 and calculated the sample proportion of red chips. And the question says, how well does the sample proportion estimate the true proportion of red chips? So if you remember, this was a graph where, or a population where half the chips were red and half the chips were blue. And it says, note that the center of the approximate sampling distribution is close to 0.5. And in fact, if we took all possible samples of size 20 and found the mean of those sample proportions, we would get exactly 0.5. So since the values from the sampling distribution accurately reflect what the value of the population is, what we would call that statistic is an unbiased estimator. And an unbiased estimator is what we're hoping to get when we're trying to estimate a parameter. So if an unbiased estimator, if the mean of its sampling distribution is equal to the true value of the parameter, we would say that that statistic is an unbiased estimator. So if this was in fact our sampling distribution from that problem, we would say that it is an unbiased estimator because the center of this graph appears to be around 0.5, which is in fact what the value of the parameter is. So in terms of some other things we're going to describe, and we talked about this in class, about how one of the things that we're looking at when we're talking about sampling distributions is we want to have low variability, because low variability yields more consistent results. So if you notice here with this, and I just have two different graphs here, both of which have sample sizes of 100, but if you notice, this one has a sample size of 1,000. What you notice here is that this graph here has less variability than this graph here. And part of the reason for that is because of the sample size. Whenever you have a sample size that's larger, what that tends to give you is, and this says here, a clear advantage over smaller samples. And the reason for that is because larger sample sizes yield less variability. So whenever we can increase our sample sizes to get more accurate results, that's always better than having a smaller sample size, as you can see in those two graphs there. So in terms of the variability of a statistic, okay, the variability, and this is, we're measuring variability, we're measuring this as, once again, spread, and typically we measure spread using standard deviation, but the variability of a statistic is described by the spread of its sampling distribution. And this spread is determined primarily by the size of the sample, and as we said before, larger samples give smaller spread. The spread of the sampling distribution does not depend on the size of the population, which is a common mistake people make. Okay, they think that the population size determines the spread. It doesn't. It's the sample size that determines the spread of the sampling distribution. And a key note here, as long as the population is at least 10 times larger than the sample. And that's the whole 10% rule that we talked about when we were looking at binomial probabilities. So a question here, and it says the histogram above shows the intervals, and this is on the left, shows the intervals between eruptions of the Old Faithful geyser in Yellowstone Park for all 222 recorded eruptions during a particular month. For this population, the median is 75 minutes for 500 random samples of size 10 are taken from the population. The 500 values of the sample median are displayed in the histogram above on the right, so that's this here. The mean of the 500 sample median values is 73.5. So the question here says, is the sample median an unbiased estimator of the population median? So we would say here that it does appear to be an unbiased estimator because the mean of the 500 sample medians was 73.5, where the median was 75. So since these values are very close, we would say that the median appears to be an unbiased estimator. So the question number 2 says, suppose we had taken samples of size 20 instead of size 10. Would the spread of the sampling distribution be larger, smaller, or about the same? So remember that the spread of your sampling distribution is directly reflected by sample size. So if we were to go from size 20 to size 10, what would happen here is the spread, in this case, would become larger because you're decreasing your sample size. So just note the relationship there between sample size and spread. Bigger samples, smaller spread, smaller samples, larger spread. And then finally here it says, describe the shape of the sampling distribution. Explain what this means in terms of overestimating or underestimating the population median. So the sampling distribution for this, if you go back to the original graphs that I showed you, is slightly skewed to the left. And what this means is that it will underestimate, because it's skewed left, it will underestimate the population median. So just remember, when your graph is skewed left, the mean gets pulled to the tail. So the mean will actually be less than what the median is. So in that case, because it's less than, it underestimates slightly, in this case, what the population median would be. So in terms of just some other things involved with sampling distributions, one of the things that sort of illustrate here in terms of what's called bias is I'm going to kind of show you some different things like in regards to a bullseye. So when we're talking about bias, now in previous things that we did with bias when we were talking about samples, bias referred to when you had a sample, did the way a question was worded, for example, or the way that you did your sample, did that lead you to get results in one direction or another? For this here, when we're talking about bias, we're talking about something a little bit different. And for bias, what we're talking about here is more or less accuracy. So you can see here in this first graph that we have in letter A, that you have high bias and low variability, meaning you have your points that are all seem to be clustered around sort of a common place, okay, and the variability is low, meaning that the points are all seem to be sort of in one sort of spot there. This right here has low bias and high variability. This graph here has high bias and high variability, and this graph here has no bias and very low variability. So bias, if you note over here, that refers to how much our aim is either consistently on or off, and variability kind of refers to, you know, where do your points seem to arrange themselves. So I think a bullseye here, in terms of sort of illustrating what those are, I think give you a pretty good idea of the differences between those two terms there. So the lesson about center and spread, very clear here. Given a choice of statistics to estimate an unknown parameter, you want to choose one that has little to no bias and as low variability as possible. So we want to be consistently around the target as much as we can, and we also want to have our points arrange themselves in a way that are as close to each other as possible. So some other things with sampling distributions, and this is in regards to shape. Sampling distributions can have many different types of shapes, and the same statistic can have sampling distributions that have different shapes, and that all depending upon the population distribution and the sample size. So when you're talking about shape, be sure to consider the shape of the sampling distribution before you make any conclusions about the graph that you have. So just kind of finishing up here with some different things with sampling distributions, and this was just some different formulas that that I came up with in regards to the German tank problem and the corresponding sampling distributions that go with them. And the question here at the end says, which statistic gives the best estimator and why? So remember what we're looking for when we're talking about the best estimator. We're talking about low bias or no bias at all, and very little, as much small variability as possible. So for each of these different graphs, you can see here the variability that they have, with the exception of this graph here, seems to be roughly the same. These four graphs here seem to have variability that's very similar. But if you notice, this first graph here has a clear shape that appears to be roughly symmetric, where most of the points seem to sort of cluster themselves around this line right here. Okay, and this formula here is the formula that I gave you, that the government came up with for what they were estimating. So this graph right here is the one that you would say gives the best estimator, because it has the most values that seem to hover around what the actual value is. So we would say that this is the best unbiased estimator of the 5 different graphs there. So what we're going to get into looking at in the next couple lessons has to do with some different things that are involved with sampling distributions in regards to categorical data. So we're going to take a look at some different things involving P and P hat. And then we'll also follow that up with some different things with sampling distributions involving quantitative data. And that's when we're talking about mu and X bar and all the different things that go with each one of those.